Well, hello there, good people. Today we are going to be talking a little bit about radioactivity. Now, I don't think I really truly understood radioactivity until I actually started teaching physics. I knew that radioactivity was something that was bad, like you didn't want radioactive stuff entering your life, but I didn't really totally know what it was. Well, today we're going to talk about what radioactivity is and what causes it, and also why it's not good for you and why it's bad for your body and dangerous and all of those kinds of things. We'll start today by talking a little bit about the discovery of radioactivity. And to start, we're going to need to start with a character by the name of Henry Becquerel. Mr. Henry Becquerel did a little experiment actually on accident. You see, Mr. Henry Becquerel had some photo paper that he had lying around. Now, if you know anything about photo paper, here's what you know. You know that photo paper is made so that when it gets exposed to light, it turns black. So the whole photo paper is actually white, and then it's coated in this layer of chemicals that are all photosensitive chemicals. So when those chemicals get hit by light, then those little chemicals will turn black in the spots where the light hits them. You could see how this would be very helpful for capturing images because what you can do is if it gets exposed to light, the places where the light does hit it turn black, and the places where the light doesn't hit it stay white. So Henry Becquerel had a little piece of photo paper. Now, if you've ever had photo paper before, like if you've worked in the Devil in Dark room before, then you know that you don't want to just leave photo paper sitting out in the room in the light, because then the whole photo paper will turn black. So what you do is you take your photo paper and you put it in these really special light tight bags that keeps the light from getting into the photo paper so that the photo paper stays white unless it gets exposed to light. Now, Henry Becquerel had a piece of photo paper and he had it underneath a piece of black light tight paper. Let me show you here. 1 second. Okay. And I'll blow this up a little bit so that you can see it. Yeah. Okay, here we go. So he had a piece of photo paper. This actually is not photo paper. This is just plain paper. Otherwise, I wouldn't have it out in the light. He had a piece of photo paper like this. And then on top of that piece of photo paper, he had a piece of black paper that was protecting it from the light so that it was not exposed to light. And then on top of that, he put a little rock like this. And now that little rock was sitting there for quite some time, and then all of a sudden Henry Becquerel said, "Hey, where did my photo paper go?" And he said, "Yes, here it is." And he picks up the little rock, and he picks up the piece of black paper, and and he finds this little piece of photo paper, and on his little piece of photo paper is a dark spot where the rock used to be. And so he says, "Well, isn't that mysterious? Photo paper turns black when it's exposed to light." But he says this paper wasn't exposed to light at all. It was exposed to a rock. And he says, "Well, okay, this is very interesting. Is this rock emitting some sort of light? Perhaps a light that I can't see. Or maybe it's emitting something else." And he said, "I don't know what's coming out of this rock, but something is being emitted by this rock that was hitting the photo paper and telling the photo paper, hey, something is here." And so that began the long quest to find out what is coming out of the rock. What is the rock spitting out into the world that is then hitting the photo paper and making the photo paper change colors? That was the main quest of the day. So Henry Becquerel found this all out about a rock. And then, just a few years later, a woman by the name of Marie Curie, one of the most famous female scientists, Marie Curie started to do her own experiments with magic rocks. And here's what Marie Curie did is she took her own pieces of photo paper and she took her own rocks and she kept doing this experiment over and over again where she would put the rocks in different situations on top of the piece of photo paper and see what kind of image showed up on the other side. Now, the first experiment that she did, the very first experiment, was she took the rock and she heated it up a lot. So she got it really, really hot and then she put it on the photo paper. Then she took the rock and she cooled it down a lot and then she put it on the photo paper. And then she wanted to see which one made a darker spot, the one that was heated up or the one that was cooled down. And it turns out that both rocks made the same amount of darkness. So she said, that is very interesting because it appears then that the rock makes the same or puts out the same amount of stuff into the world regardless of how hot or cold it is. Now, this to us sounds like no evidence, and you would say, Miss Wilson, she got no results, and that is completely unhelpful. But sometimes having no evidence actually is very helpful. And here's why it was very helpful for Marie Curie, is she said because the temperature doesn't affect it. Whatever this rock is putting out into the world that's turning the photo paper black, whatever it's putting out, has nothing to do with the speed of the little atoms that are zippy-zapping around inside that rock. It has nothing to do with speed. So this seemed actually very important. So important that she wrote it down, and you should too. Her first experiment, and I would write this down like right here, but I'm not going to write it all down because it's actually going to take me a really long time to write it down, and then you'd just be sitting here watching me write it down, and that would be boring. So this is what you will write down, is you'll write down that her first experiment showed the temperature, which means the kinetic energy of the particles. The kinetic energy of the atoms had nothing to do with the radiation or with the stuff that was coming out of the rock and turning the paper black. The speed or the kinetic energy of the atoms had nothing to do with it. So that was her first experiment. Here was her second experiment. Her second experiment was she took this little rock. This rock happened to be a piece of uranium, and she did some like little chemical experiments with it. She combined it with some other elements. She did a lot of chemistry to make it into a new alloy, so that it wasn't just aluminum. Now it was aluminum combined with other stuff. And when she had aluminum combined with other stuff, or when she had, uranium combined with other stuff, then she took that uranium combined with other stuff, and she put it on top of her piece of photo paper, and she saw what happened. Then she took some more pure uranium, put it on top of the piece of photo paper, see what happens. And both times she put that uranium on top of the piece of photo paper, when she looked at the photo paper, there was a black spot. So she said, interesting. No results. But sometimes no results are results. And so here's what she found. She said, there's the bell. She said, if there are no results, that must mean that whatever is leaking out of the rock, whatever sort of radiation is coming out of this rock, it must have nothing to do with the chemical composition. It must have nothing to do with the chemical bonds of this little rock. It has to have nothing to do with chemical bonds. And it also probably has nothing to do with electrons, because electrons are what create chemical bonds. So she said, I know that it's not about the temperature, it's not about the kinetic energy of the atoms, and it also has nothing to do with the chemical bonds or the electrons in the atoms. This led Marie Curie to conclude this idea, that whatever it was that was leaking out of the rock, whatever it was that was coming out of the rock, whatever it was that was radiating out of the rock, must have had something to do not with the electrons, not with the kinetic energy of the atoms, but with the nuclei in the atoms. Because the nucleus of an atom is not impacted by temperature, it's not impacted by how fast it's moving, and it's also not impacted by chemistry, because chemistry is all about interactions between electrons. So she said, whatever is happening here has to be coming out of the nucleus of the atoms. That was Marie Curie's big idea. Now, that was very good, because then we'd made some progress. We knew that whatever was coming out of the rock had to do with the nucleus of the atoms in the rock, but it had nothing to do with the chemical composition of the rock. But we still did not know what it actually was. Now, there was a guy who tried to figure out what it actually was, and his name was Ernest Rutherford. You remember him from yesterday. Ernest Rutherford. Now, here was Ernest Rutherford's idea. He had heard about Marie Curie's work. He said, okay, I know that whatever is turning the paper black is coming from the nucleus of the little atoms inside the rock, but I don't know what it actually is. So Ernest Rutherford designed an experiment, and the experiment that he designed looks something like this. Let me go ahead and draw a picture of it. Actually, I'm going to go gray here. Ernest Rutherford made a giant lead box that looked kind of something like this, a giant lead box. And he cut a little hole, not a giant hole, he cut a little hole in the side of his giant lead box, like this. Then, outside of the lead box, he made a giant magnetic field. So let's draw a magnetic field here. Let's say that the magnetic field is red. Okay. Well, it's a light pink for today. He has a magnetic field, and that magnetic field is going into the screen as you see it here. Now here's what he did, is he took one of those little magic rocks, one of those little rocks that was turning the photo paper black, he took that little magic rock and he put it right here in the little lead box in the little opening that he had made. And here was his idea. His idea was that basically the little lead box would act as a little aimer so that it would aim the radiation. I kind of want to re-scribble that. You guys are like, you are the worst, Miss Wilson. Just scribble and move on. Scribble and move on. Okay. Scribble, 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 scribble. Yay. Okay. He said basically that the lead box was going to act as a little aimer. So it was going to aim all of the radiation, all the stuff, whatever it is that's coming out of this little rock. It's going to aim it all so that it all goes this way. You can see that that radiation can't go this way or this way or this way, because if it goes any of those three ways, then it'll get stuck in the lead. So instead, his little lead box, can you hear all the music outside? I kind of hope you can. It's like very exciting outside. So instead, all of the radiation, whatever was coming out of this little rock, would be launched this way because the lead would force it all to go that way. Now, here was his idea. His idea was that when this radiation got out here, that radiation would do one of three things. And if it did one of these three things, it would tell him something about what this stuff is that's coming out of the little rock. He said, I know something about Unit 11 because I remember Unit 11. And he said, I remember my right-hand rule, and I remember things about electricity and magnetism. He said, I remember that if I point my fingers in the direction of the magnetic field, in this case, into the screen, my thumb points the way that this little thing is going, which in this case, it is going to my right. Wait, my right, which is this way. I don't know what that looks like for you. Maybe like this way? I don't know if this is helpful. Yes, okay, this works. So he said, if it's going to the right and the magnetic field is going into the screen, this is really hard to show actually. I don't really know how to show this in a way that you can see it. But anyway, you can use your own right-hand rule. Whatever it is going right. Magnetic field is going into the screen. He said that means that a positive charge is going to get pushed up. And so he said, if this stuff comes out positive, if the stuff that comes out here is positive, then it'll launch up like this. Then he said, using his right-hand rule, he said, back of my hand, if the stuff that comes out of that little thing is negative, then it's going to go down. It's going to get shoved down. And he said, and if the stuff that comes out of that little thing is neutral, then it'll go straight. So that's what he proposed. Now, he put the little rock in. He put it in his little lead box. He started up the magnetic field, and the radiation took a turn like this. And he said, aha, that means whatever coming out of the rock is positive. But then he actually traded it out for a different rock. So then he put in a different kind of rock that also turned the photo paper black. But now this is a different rock entirely. And we put in this rock. Then when the little radiation came out, then it didn't go straight. It didn't go curve up anymore. Now this radiation curved down. And he said, oh, interesting. So he put in a third rock. And the third rock that he put in also made the photo paper turn black. But this time when he put in the third rock here, the radiation, whoa, let me try again. The radiation came out of the little third rock here, and it went just straight like this. And he said, well, would you look at that? It looks like there's not one type of radiation, but that there are three types of radiation. In other words, different rocks will put out different things into the world, and those different things all turn the photo paper black. But there are three types of radiation. Now, if you were Ernest Rutherford and you had no idea what these three types of radiation were, but you just knew that there were three types of radiation, here's what you would know. You'd know that there's this one type of radiation, and this first type of radiation is always positive. You'd know there's a second type of radiation, and this second type of radiation is always negative. And then you know that there's this third type of radiation, and this third type of radiation is always, wow, that is just an enormous, like, obtrusive circle. Okay, this third type of radiation, he said, is always neutral. He said, I don't really know what these types of radiation are. All I know is that this first one is positive, the second one is negative, and the third one is neutral. Well, hey, here's what you know. You know, sorry, I'm going to erase all of these names. Thank you, names. You have served us all very well. It's very, oh gosh, oh no, not the box. Keep the lead box. Oh no, now it's going to have to undo all that, and we're going to have to redo it all again. Tragedy. Or, wow, we might get stuck here for a second. One moment, please. Okay, that's much better. So, Ernest Rutherford said that there were 3 types of radiation. Now, if there were 3 types of radiation and all you knew is one is positive, one is negative, and one is neutral, then you would probably call them different things. Like maybe you'd call the first one radiation 1. You'd call the second one radiation type 2, and you'd call the third one radiation type 3. Or you could call them like radiation A and radiation B or radiation C. But if you're a scientist and you have a strange affinity for the Greek alphabet, then you could actually name them these things. You could say, okay, well, the first type of radiation I shall call radiation alpha. Alpha. That is crazy. Radiation alpha. You would say the second type of radiation I shall call radiation beta. And the third type of radiation I shall call radiation gamma. And that would be like your A, B, C's of Greek. And this would be very convenient for you because then you could label alpha radiation with the Greek letter alpha, beta radiation with the Greek letter beta, and gamma, whoa, that's a terrible beta. Let's try that again. Back. Take 2. Beta. That looks much better. And gamma radiation with the Greek letter gamma, like this. So there are 3 types of radiation: alpha radiation, beta radiation, and gamma radiation. And he said whichever one you get depends on which type of rock that you have or which type of substance that you have, whether it emits alpha, beta, or gamma. And he said, I don't really know what these things are. All I know is that alpha is positive, and beta is negative, and gamma is neutral. He said, that's all that I know. Now here's the thing. Ernest Rutherford did not know what these 3 types of radiation were, so that's why he called them alpha radiation, beta radiation, and gamma radiation. He didn't know what these like little particles that were flying out of this rock actually were, so he made up names for them. However, you know something that's positive, yes? What is something that is positively charged? You say, Miss Wilson, a proton is positively charged. Yes, that's what alpha radiation is. Alpha radiation is little protons that come zippy-zapping so very fast out of the little rock. That's all that alpha radiation is. Except that normally these little protons come with friends. So normally, what you actually see is 2 little protons that go zippy-zapping out with 2 little neutrons. So what you see, we like to say, is a helium nuclei. That little helium nuclei comes zippy-zapping out of this rock, which is really a longer way to say it's 2 little protons and 2 little neutrons. That says neutrons, by the way. I know it's super legible. Yeah. So you get 2 little protons and 2 little neutrons that come zipping out. But that's all that it is. Little alpha radiation was just 2 protons and 2 neutrons that come flying out of this rock. Now, beta radiation, Ernest Rutherford didn't know what it is, but he knew that it was negatively charged. Hey, you know something that is negatively charged? You say, Miss Wilson, an electron is negatively charged. So true. All that beta radiation is beta radiation is little electrons that come flying out of this little rock. And lastly, gamma radiation is neutral. Now, there are a lot of things in the world that are neutral. So this one's a little bit trickier, but one of the things that is neutral is a little photon. Whoa, I just like my T and my O just got merged. Gamma radiation is a little photon. Hey, do you remember the last time when we talked about the electromagnetic spectrum and we had that whole wave that went all the way across the screen or all the way across the board if you were in class, and you saw, hey, that gamma was the highest frequency type of electromagnetic radiation, but really it's just kind of like a form of light that's really, really high frequency light? Yeah, that's what gamma radiation is. Gamma radiation is just really, really high frequency light particles, little high frequency photons. And that's all that it is. So he said this little rock is either spitting out alpha particles, 2 protons and 2 neutrons, beta particles, electrons, or gamma particles, which are just little photons. And so that leads us to the 3 types of radiation. Now, I like to ask students, hey, which type of radiation is dangerous for you? Which one is no good for you? And they say, yes, Miss Wilson, all 3 are dangerous for me. None of them are good for me. And that is absolutely true. Alpha radiation, beta radiation, and gamma radiation are all not good for you. All of them do what we call ionization. So all 3 of these here, let me get that word up here. All 3 of these will ionize atoms. Ionize just means they'll knock a little electron off. Here's what I want you to imagine. Imagine an alpha particle, a helium nucleus, 2 protons and 2 neutrons, moving at very, very high speeds, comes flying towards a little atom that is sitting there all innocently, just kind of wandering and meandering and doing its little thing. You throw a little alpha particle at that thing will come in like a cannonball, and it'll wreck that thing. It'll literally shove electrons off of the atom. It'll ionize that little atom. Beta particles, same thing. Beta particles are much, much smaller. They're just electrons. They're teeny, teeny, tiny in comparison to your alpha particles. Your alpha particles are massive compared to your beta particles. You got 2 protons and 2 neutrons. Electrons are so very small. Those little electrons come in. They come whizzing into a little atom. The little atom looks up unsuspecting, sees a little electron coming towards it at a very, very high speed. That little electron at a very, very high speed acts like a bullet. It's small, but it'll certainly do some damage. That little electron comes zooming in and it'll knock little electrons off the atom. Same thing as an alpha particle. Gamma particles, those don't have any mass, but they do have a lot of energy. That thing is kind of like getting hit by a lightning bolt or getting hit by something, like just getting zapped. What happens is a little unsuspecting atom is kind of sitting there. That little unsuspecting atom gets hit by a gamma photon, and when it gets hit by a gamma particle, it gives it so much energy that it zaps little electrons, and the electrons go flying off that thing. So all 3, alpha, beta, and gamma radiation are all very dangerous. You can imagine that you would not want alpha particles, beta particles, or gamma particles to be running into any atoms that happen to live inside your cells. Do you see how that could be very dangerous for you? You particularly do not want them hitting any of the atoms that happen to live in the very important parts of your cells, say like your DNA. Do you see how that could be very, very problematic if any of these little particles went running into one of the atoms that makes up your DNA? That could absolutely destroy your DNA, and that would give you cancer. So yes, that is why these little particles are very, very dangerous. If students are always asking, Miss Wilson, which one is the most dangerous one by far is gamma radiation. Partially because it's so energetic, it has so much energy, but also in part because it's very, very hard to shield. An alpha particle comes at your cells like a little cannonball, but you can kind of block a cannonball with like lead or other materials. Beta is a little bit harder to block, but lead will still do a good job of not letting it through. Gamma radiation can get through anything. So that thing will just bullet right on through and has no problem making it to your cells. So those are the 3 types of radiation, and yes, they are all dangerous. This is why Marie Curie actually died after her work with uranium, because she got radiation poisoning from always working with the uranium all the time. She was constantly exposing herself to radiation and had no idea at the time. So 3 types of radiation, all of them are dangerous for you. Alpha radiation is just a long way of saying you got 2 protons and 2 neutrons that are getting spit out of the rock. Beta is a fancy way of saying you got some electrons that are getting spit out of the rock, and gamma is a fancy way of saying you got photons that are getting spit out of the rock. But those are your 3 types of radiation. Now here's the next question for us is these are what the 3 types of radiation are, but why do they happen? Because it's not as though every rock is always spitting out alpha radiation, or every rock is always spitting out beta radiation, or every rock is always spitting out gamma radiation. And it's not like the little oxygen molecules in the air. The oxygen molecules in the air, those aren't throwing little alpha particles at you all the time. That's not true. So it seems like it's only some types of materials that are doing this, and only in specific conditions, not all the time. So let's talk about what causes each of these types of radiation. I'm going to go ahead and pull up a new little slide here. One moment. Okay, here we go. Why do each of these types of radiation happen? Let's start with alpha decay. Alpha decay happens because the nucleus is too big. Now, in order to understand why this happens, you need to remember the 4 fundamental forces. Our 4 fundamental forces are, in order of strength, first, gravity. Second, the electromagnetic force. Third, the nuclear weak. And fourth, the nuclear strong. Sorry, I do hope you can read those like a little bit. Gravity, electromagnetic, nuclear, weak, and nuclear strong. Now, alpha decay happens when the nucleus is too big. Let me show you a little bit about what this looks like. Suppose that you had a little nucleus that looked something like this with a gajillion little protons and neutrons. And by a gajillion, I mean like maybe like 90 protons. Something in the realm of like 200 little subatomic particles living here in the nucleus. Okay, now here's the idea. Some of these are protons, some of them are neutrons, and none of them are electrons. Wow, that was crazy that I almost just said that. Okay, so we have protons here and here and here, and let's call this one a proton, and let's call this one a proton. And let's add another one here. We'll call this one a proton here. We'll say that about half of these should be protons, roughly. You probably have a few more neutrons than protons. But the general idea is that you have about half protons and half neutrons. Okay, now here's the idea. The idea is, okay, yeah, we'll call that in. Here's the idea. The reason why the nucleus stays together is because of the nuclear strong force, which holds everybody together. Now, here's what you need to know about the nuclear strong force, is the nuclear strong force is not like gravity or the electromagnetic force. Gravity and the electromagnetic force are what we call action at a distance forces, which means the two things don't have to be touching each other in order for them to influence each other. Like the Earth can pull on the moon by gravity without the moon touching the Earth. Or like a little proton could push on a little electron or pull on a little electron without them ever touching each other. The nuclear strong force is not like this. The nuclear strong force is like glue. You have to be touching in order for it to stick. But if they are touching, it's really very, very strong. So the nuclear strong force works to hold things together. Let's look at a little example here. Let's look at, yeah, that little guy. That looks good. So this little proton right here, doop, doop, this one here, this little proton is held to this little neutron right next door, this little proton right next door, and this little neutron right next door, and maybe possibly this little neutron right next door, but probably closer to those ones because it's actually in contact with them. And the nuclear strong force holds together those little protons and neutrons that are in contact with each other. So it holds them together. But this little proton right here is definitely not feeling a nuclear strong force with this little proton all the way over here because they're way far apart from each other. But what it is feeling from this little proton over here is the electromagnetic force, because the electromagnetic force is an action at a distance force. Now this little proton right here and this little proton right here and this little proton right here and this little proton right here are actually all repelling this little proton and trying to push it away. But the proton stays there because the nuclear strong force is stronger than the electromagnetic force of repulsion that's pushing it away. That is true when the nucleus is small. But when the nucleus gets really big, you're basically just adding way more protons as this thing gets really big. And so you're adding, pretend that this is like clear and you can actually like coherently read it. What you're adding is you're adding way more protons. If you add way more protons, you increase the strength of the electromagnetic force that is repelling this little proton. But the nuclear strong force doesn't get any stronger because the nuclear strong force is only with this little proton and the little guys who it's touching. So the nuclear strong force is just as strong, but if you get too many protons here, now you have a gazillion protons, and by a gazillion, I mean like 90. You have like 90 protons who are pushing on this little proton right here. And if you have enough protons pushing on it, then the the electromagnetic force will be greater than the nuclear strong force that's holding it there. And this little positive charge right here, this little proton will get pushed out of the atom. But if it gets pushed out of the atom, it's not going to go by itself because the nuclear strong force is holding it to its buddies. So that little proton is going to get pushed out of the atom with all the little guys who it was right next to. So it's going to get pushed out with this little proton here and two little neutrons. This is why we get alpha decay. This right here is an alpha particle. It's two protons and two neutrons, or what we call a little helium, because it has two protons and two neutrons. And it occurs because the nucleus got too big, so the electromagnetic force got bigger than the nuclear strong force. Now, you could imagine that this is not true for every single element out there in the world. Like, not every single element is going to experience alpha decay. For example, oxygen is never going to experience alpha decay because oxygen is a relatively small atom, and so the nuclear strong force will always be greater than the electromagnetic force because there aren't enough protons there to push the protons off. But when you get to really big atoms, the really big elements, those are the ones where you actually get alpha decay. Let me pull up a periodic table here real quick, one sec. Okay, here's my little periodic table. Shout out to Google for providing this periodic table for us. If you look at the periodic table, things start to get a little too big right in this lead bismuth kind of area. Like right in here is where things start to get too big. So before that, like mercury is totally stable. You're not going to have a lot of alpha decay. Thallium is also pretty stable. Lead is pretty stable. Bismuth is mostly stable. And then when you get to polonium, everything above that, all of these numbers above that are way too big. And so those ones will actually experience alpha decay. This is why for a long time there were a lot of elements up here in the really big numbers that we actually just had never seen before. We knew that they existed in theory, but we'd never seen them before. And the reason why we'd never seen them before is because they are so unstable that if you try to make one, the moment you try to make it, it alpha decays and that thing isn't the same element anymore. It'll decay into one of these smaller elements here. And so for a long time, we never had any of these really big elements, and we had like names for these elements like ununium and things like that, where it was just like, well, we don't have this one yet, so we don't really have a name for it because we've never seen it before. And that was because these elements are so unstable that they're just really, really hard to create, and you can't really get them to push together because of that electromagnetic force. So that's the main idea with alpha decay. Alpha decay, notice, does not happen with all of the elements. It only happens with the really big ones. And now back over here to our drawing. That's a little bit on alpha decay. Let's talk beta decay. Beta decay occurs primarily because you have, hang on. Beta decay happens because the nucleus is two, what we call neutron rich. The nucleus is too neutron rich. Hey, you remember, if you went back to our other page, that we said a beta particle is just a little electron. But Marie Curie said, yeah, it turns out that actually this radiation stuff has nothing to do with the electrons. It only has to do with the nucleus. So this is a problem for us because we say beta decay, well, isn't that an electron? And electrons don't come from the nucleus. Or do they? It turns out an electron can come from the nucleus. And let's see how that would happen. First, this is a little bit of background information, and this is not stuff that you really need to know, but I'll touch on it very, very lightly. We got to talk about the nuclear weak force. The nuclear weak force, you should know, is responsible for making a proton or a neutron a proton or a neutron. You know, I'm going to erase this little atom here. Bye, atom. You know that atoms have parts to them, that an atom is not just a little billiard ball, but you know that an atom has parts. It has a proton, it has a neutron, and it has an electron. Well, same thing is true with little protons and neutrons. Protons and neutrons are not just little billiard balls. Protons and neutrons also have parts to them. And the parts that make up a proton and a neutron are called quarks. So inside every proton and a neutron, if you could zoom in on a proton and a neutron, you would see a quark. Let me go ahead and get this up here. You would see a quark, or actually multiple quarks. Quarks are what make up protons and neutrons. There are two types of quarks that you need to know for today. Actually, there are lots of types of quarks, but there are two that you need to know. There are quarks that we call up quarks, and there are quarks that we call down quarks. Now, these names for quarks are totally arbitrary. We have to have a way of talking about this quark and this quark. And we said, what shall we name them? And someone said, well, let's call this one an up quark and this one a down quark. And everyone was like, okay, sounds good. It doesn't mean anything about direction. It's just two different names for quarks. So one of them is named up, one of them is named down. Goofy names, but there you go. A proton, if you zoom in on a proton, you would see that inside of a proton, you have 2 up quarks and 1 down quark. And if you've zoomed in on a little neutron, you would see that a neutron is made up of 2 down quarks and 1 up quark. The nuclear weak force is responsible for making the quarks the kind of quarks that they are. So it's responsible for making up quarks, and down quarks. Now, it turns out that actually the configuration down quark, up quark by itself is a kind of unstable configuration, and the nuclear weak force would like to undo this. Up quark, down quark, that is actually a pretty stable configuration, but down quark, up quark, that's not a very stable configuration. So if you have a little neutron by itself, the nuclear weak force will actually make this neutron decay, and it will change what the quarks are like inside of the neutron. And the neutron won't stay a neutron for very long. Now, this happens if a neutron is by itself. If a neutron is by itself, then it'll probably decay like in about 8 minutes. I should say that you have a 50% chance of having a neutron still be a neutron after 8 minutes. After 8 minutes, you have a 50% chance it's become a proton and an electron. But neutrons by themselves aren't very stable. If you put a neutron in a little family, if you put it in a little nucleus, in a little communal home, and you put that neutron surrounded by a bunch of little protons and a bunch of other little neutrons, and it has a nice little loving family, and it feels very well loved and safe and supported, then it'll be a much more stable neutron. And it can actually stay a neutron for a very long period of time, because a nuclear strong force kind of squishes things together a little bit and holds it in there. But if you have a neutron sitting all out by itself, well, then it's not very stable and it'll decay very quickly. This means if you have a nucleus that has too many neutrons, those neutrons start to feel a little shaky and unstable. They don't feel as supported by the proton home. And so because there are just neutrons by themselves, those neutrons become unstable. When those neutrons are unstable, the nuclear strong force will cause the neutron to actually lose its neutronness by changing its quarks. Now, I'm about to tell you something that is not actually true, so please do not let anyone, if anyone comes up to you and says, hey, did your physics teacher tell you this? You would say, no, she definitely did not say that. She would never say that because that is not true. But what it is it's a helpful way of thinking. So here's something that is not true, but is a helpful way of thinking. You can think about it this way. You can think about a neutron as kind of being a combination between a proton and an electron. Doesn't a proton have a positive charge? An electron has a negative charge. You put together a positive charge and a negative charge, and you get a neutral charge. And so you can kind of think of a neutron as being like a combination between a proton and an electron. So what happens is, if this neutron is unstable, it will decay. And when it decays, one of its down quarks will turn into an up quark, and it'll become a proton. But in the process, it'll also split and release an electron. Again, not a great way of thinking. You really should not think of a neutron as being a combination of a proton and electron, but it is a helpful way to think. So you can imagine that this little neutron here, if a little neutron gets unstable, one of its quarks will become an up quark, and then it will become a little proton. But in the process, it will also emit a little electron at the same time. And also, this is something that you need to know, but you don't really need to know much about it. It will also emit at the same time a third kind of particle. It turns out that quarks and electrons and protons and neutrons, those aren't the only kind of particles in the world. There are other kinds of particles too. It'll emit a third kind of particle that we call an antineutrino. You really don't need to know much about it. It's really not that essential. It doesn't have a charge. You can kind of think of it as like the neutron just kind of spits out a little bit of energy there. But it does emit a third particle that's kind of inessential that, again, we won't talk about much today, called an antineutrino. So the neutron, it becomes a proton, releases a little electron, and releases a little antineutrino like this. And now you have two particles, a proton and an electron, where you used to have one. Here's what happens. If this is inside of a nucleus and that neutron becomes a little proton, now that proton is already living in the nucleus and it's already bound to its friends by the nuclear strong force. So the proton will stay in the nucleus. But the electron is not held in there by the nuclear strong force. So the little electron will go zooming off into space. And that little electron that goes zooming off, that is a beta particle. So here's the main story of beta decay. Here we go. Synopsis recap. The main story of beta decay is that a neutron will decay into a proton and an electron. The proton will stay in the nucleus, and the electron will go zippy-zapping off, and that electron is what we call beta decay. That is the essence of why beta decay occurs. It occurs because the nucleus is too neutron-rich, and one of those neutrons becomes a proton and an electron. The last type of decay is, wow, that was a terrible 3. The last type of decay, oh no, I just don't like my circles. I'm so sorry. Oh gosh, you guys are like, Miss Wilson, just chill. It's really fine. It's not a big deal. Your circles don't really matter that much. We can still learn even if your circles are bad. I get that. I totally get it, but I still had to redraw it. Gamma decay. Gamma decay happens when the nucleus has too much energy. That doesn't really look that doesn't really look like the word energy. Try again. Try again. Energy. When the nucleus has too much energy, then you get a little bit of gamma radiation. Gamma radiation is just a photon. It's basically pure energy. It doesn't have any mass. And so when gamma radiation happens, you basically have a nucleus that has way too much energy, and it just goes, and it spits out a little photon. That little photon goes zooming off. It carries a lot of energy with it. Now the nucleus has less energy, and it feels much more comfortable and says, okay, this is much more stable position. Now, gamma radiation oftentimes sometimes it's by itself, but gamma radiation will oftentimes accompany beta radiation or alpha radiation. So when you have some beta decay or some alpha decay, you'll also get a little gamma photon that gets emitted at the same time. So that is something that you'll see occasionally. Now here's what you see with most certainly alpha decay and beta decay, is that in the case of alpha decay and beta decay, you have a element that then either loses protons in alpha decay or has a neutron that turns into a proton in beta decay. Do you see how in both of these, the element actually becomes a totally new element? It's not the element that it used to be anymore. Well, in order to express this, we have what we call transmutation equations. And transmutation equations will show you how one element will turn into another element because of radioactive decay. Let's go ahead and look at some practice ones. I'm going to show you 4 little practice equations here. The first practice equation is going to be alpha decay. The second one will be beta decay. And then the third one will be gamma decay. And lastly, we'll do a little, whatever it's called. Wait, hang on. Artificial transmutation. Okay. Transmutation basically means, hang on, transmutation. Yeah. Done. Transmutation basically means that one element is becoming another element. So let's go ahead and take a look at an example. Let's start with an example of alpha decay. In alpha decay, let's start with an element that most certainly would undergo alpha decay, something very, very large. Oh, look at this one. How about this one? It's called radon. You can see that it's named radon literally after radioactive decay because that is how often it radioactively decays. Okay, so here's radon. It is very unstable. Let's go back over here. We're going to start with a little radon atom. Now, the way that we write a transmutation equation is we start by writing the chemical symbol of what we call the parent nucleus, which is the initial nucleus before it undergoes decay. So we start with writing the chemical symbol. Then down here at the bottom, we're going to write the atomic number. If you look at our periodic table, the atomic number for radon is number 86. That is the number of protons. Then up here, Then up at the top, we are going to write the mass number, or the little atomic mass, for this particular element, or this particular isotope. So for this particular isotope, we're going to go with radon 222. So I go back over here, and I'm going to write up at the top 222, which means this particular isotope has 222 protons and neutrons. 86 of those are protons, and the rest are neutrons. Now that radon is totally and completely unstable, so it is going to decay. And when it decays, it's going to experience alpha decay because it's way too big of a nucleus. So it's going to decay into one little helium atom is going to get released. This helium nucleus, we know it's going to run away with its 2 protons and with its 2 neutrons, which total up together for a mass of 4. And now what's going to be left behind, the element that's going to be left behind, is going to have 2 less protons. So it's going to have atomic number 84 for 2 less protons. If we check up here and we check our math, it's also going to have 2 less neutrons, or it's going to have 4 total less mass. So it's going to have a mass of 218. To figure out what this element is going to be, I go back to my periodic table over here, and I look at my periodic table, and I say, which element is it that is atomic number 84? And would you look at that? It's polonium. So I will then write polonium over here. Polonium, like this. Now, polonium is what we call the daughter nucleus. It's the nucleus that results after the transmutation, after the radioactive decay. So you can see that the radon becomes a little helium alpha particle, and now it's not radon anymore, now it's plutonium. Or polonium, sorry. It's now polonium. Now this polonium, if you look at our periodic table, polonium is also unstable. So it's highly likely that this polonium would then undergo, that this polonium would then undergo its own little decay, and it would become lead. And then after becoming lead, at that point, it would probably be pretty stable. So that's the idea. At this point, because it also has such a high, do you see over here our isotope is 218, so it has 9 more neutrons than average, so it might also undergo beta decay at that point. But anyway, that's beside the point. Main point is this equation. Okay, next, let's look at another one. Let's try a beta decay example. Sodium is normally very stable, but if I had an isotope of sodium that was sodium-24, that means that that isotope would have a ton of extra electrons. Too many extra electrons ton of extra neutrons. Too many extra neutrons if you ask that sodium atom. So what will happen to it is one of its neutrons will become a proton, and it will spit out a little electron. A little electron will go flying out of here, and you'll be left with something that has 1 more proton. If this started at 11, it's going to end up with 12 protons because one of its neutrons is going to become a proton. So I am going to end up with 12 here. Now, because one of the neutrons has become a proton, the total mass number actually hasn't changed because it's still the same mass. It's just that one of those neutrons became a proton. I hope I'm saying all this right. I just realized I might have mixed up my words. So I leave this as 24. I look back at my periodic table here to see what element came of this, and I see that sodium was here. And now, because of beta decay, it became magnesium with atomic number 12. So, going back over here, this becomes magnesium. Now, the way that we label this little electron here is we say that the electron has basically no mass, which relative to like a proton and a neutron, it basically does have no mass. And then, because this little electron came at the cost of making a proton, we say that it has an atomic number of -1 because it had to create a proton in order to be here. Here's how we write these equations. I want you to notice something. Do you notice here that the number on this side has to equal these 2 numbers added together, 2 plus 84? And you notice here that the number on this side has to equal 4 plus 218? Same thing here. This number here has to equal 0 plus 24, and this number here has to equal 12 plus -1. Let's go ahead and try a little gamma decay problem, and then after our gamma decay problem, we'll talk about artificial transmutation. In our little gamma decay problem, here's what we are going to have. We start with cobalt 60. So here's a little cobalt nucleus. Now sometimes this little cobalt nucleus will have way too much energy, and so what it will do is it will release a little gamma particle. The way that we write a gamma particle is we write the gamma symbol. We say it has no mass, and it also does not come at the cost of any protons or neutrons, so we just write a little 0, or protons or neutrons. So we just write a little 0 there for protons. And then all that we're left with is still cobalt 60. You can see that it hasn't changed elements at all. It just is now cobalt 60 with a little bit less energy. So that's how you write one of those equations. This shows you our 3 types of radiation, but you can also have an element become a new element in a different way. This happens by using a particle accelerator to create artificial transmutation. In artificial transmutation, what happens is I essentially launch a little particle at another particle, and I try to get those particles to change. Let me try an example here because it's most easy with an example. And actually, I kind of want to, oh gosh, I already put everything away. That was like way too efficient of me. Don't put so many things away, Miss Wilson. Okay, I'm sorry. It was just so tempting to get everything so nice and cleaned up. Okay, let's try this one here. Wait. So sorry. Okay. Yes, let's try this one here. Here's an example that we'll do of an artificial transmutation. What we'll do, this is example number 4. This one is an oh, nope, I can spell. It's an artificial transmutation. What all that means when we say artificial transmutation is that this thing does not normally happen in like normal everyday life. In order for this to happen, we really have to set up like some sort of lab situation where we're forcing this to happen. These types of transmutations, this nuclear decay, that happens naturally. These ones, these don't happen naturally. So here's an example. Suppose that I had a little nitrogen-14 and I took a neutron in a lab and I shot the neutron at this nitrogen-14 as fast and as hard as I could. If I throw a little neutron at it, the way that I write a little neutron is I write it like this. I say a neutron has an atomic number of 0, but it has a mass of 1, like this. So say that I throw a little neutron at this nitrogen here. If I throw a little neutron at the nitrogen, one thing that could happen is that this little neutron could knock one of the protons off of this nitrogen. And so you would get a little carbon here that has an atomic number of 6 and a mass number of 14. Here's what this means. This little neutron, it came in, it hit the nitrogen, it knocked one of the protons off, and it replaced it with itself. So the little neutron got stuck to the nucleus, and it knocked off a little proton. What you're left with then is the same amount of mass because we traded in a neutron and knocked off a proton, but you have one less proton. Which means then we have to account for that little proton going flying off. So what you have is you have to have something at the end so that all these numbers add together. You have one little proton. If you have one little proton and no little neutrons, then it would have a total mass of 1. And we'd say that something that has an atomic number of 1 is hydrogen. Hey, isn't just a little hydrogen, isn't a proton all by itself considered a hydrogen? Isn't that true? Oh, gosh, there are my lights. I guess I've been sitting here for too long. So that's an artificial transmutation equation. Each of these, you can see, follows similar rules about how equations are balanced. The number on this side has to add to equal the addition of the numbers on this side, and the number of this side has to add to equal the number on this side. Now, before you go today, here are some things to review for yourself. Can you please make sure that you know what actually is radiation at the end of the day? Like we talked a lot about radiation today. What is radiation? What is radioactivity? Next, could you remind yourself, what are the 3 types of radiation and why does each one occur? And lastly, what is transmutation and how do you write an equation for it? And those are our 3 major topics for today. I hope you have a wonderful rest of your day and I will see you all next time, either virtually or otherwise. Bye, good people.